All right, let's talk about Chapter 6, starting with Mendeleev. The question says, how did Mendeleev first arrange his periodic table? And then what is the current modern-day periodic table arranged by? He first arranged it based on atomic mass, and then people started noticing that not everything lines up perfectly in terms of the properties. Remember, everything in the same group, everything in the same column going down has to share similar properties. And if you do it strictly by mass, then some things are out of place. For instance, you may end up with a noble gas in group 1, which react violently with water, and the noble gas doesn't react at all. And that doesn't belong in group 1. It belongs in group 8, even though its mass is out of order. So today, everything is arranged based on atomic number, which is the number of protons, and everything also lines up according to their properties. They all share the same properties if they're in the same group. Number 56 asks about Mendeleev and predicting undiscovered elements. How did he predict the properties? He gets a lot of credit because he predicted the properties of a few elements. And when they discovered these elements years later, they were right on the money, or he was right on the money with what he had originally predicted. And basically what he did was he looked at the elements above it and below it, or to the left and the right, and he kind of took the average and took an intelligent guess as to what the numbers are going to be or what the properties are going to be. Number 57. Metals are found on the left side of the zigzag or the stair-step line, while nonmetals are found on the right. The majority of the periodic table are metals. There's only a few of the nonmetals. Number 58, basically just asking you to go through your notes and look at the different names of the groups and what they end in. Now, group 1 are the alkali metals. They end in S1. They have one valence electron. Remember, group 2 also has two valence electrons. The group number and the valence electron should match, and you should just know what everything ends in. Group 2 are the alkaline earth, and they end in S2. Group 3 is the boron group. Now we start getting easy with the names. Boron group, carbon group, nitrogen and oxygen group. Those are all named on the top element in the group. So the boron group ends in S2P1. This is the first column in the P group, and they have three valence electrons. 2 from the S, 1 from the P, adds up to 3. Carbon groups in group 4, notice it has 2 S's and 2 P's. They add up to 4. The group number is the same as what the valence electrons should add up to. Nitrogen group, S2P3, add up to 5. Oxygen group, S2P4, that adds up to 6 valence electrons, group 6. The halogens, special name here, halogens in group 7, they all end in S2P5. They're almost at the octet. They need one more. And they have 7 valence electrons. And the noble gases, they're in group 8, and they all end in S2P6. There's your octet, S2P6, and they have 8 valence electrons, with the exception of little helium. Helium ends in S2, and it only has 2 valence electrons. Okay. All right, 59 says elements in the D block are referred to as the transition metals. Elements in the S and P block are referred to as a representative. S and P block guys are the nice ones. They represent the regular rules that we're used to. Transition, a little bit different. They don't necessarily follow the rules. These are the guys that make more than one charge. And remember, when you're looking at doing electron configuration, transition metals, the D block, they're always one level behind. So if you're in the 4th period and you're dealing with the D blocks, they always end in 3D. The D blocks are always one behind. All right, 60. Which group of elements on the periodic table are the most unreactive? The noble gases, group 8 guys. And they are like that because they already have a full outermost energy level. They don't need to lose, gain, or share electrons to get that octet. They already have it, so they're not interested in losing, gaining, or sharing electrons. Number 61. What's meant by the shielding effect? Which atom would have a greater one, lithium or cesium? Now, shielding effect is kind of like the kids in the back of the classroom getting away with stuff because the teacher can't see them. Because there's so many kids in the way. All the kids in the way, blocking the teacher's view, are considered shielding the teacher from the kid in the back, or vice versa, the kid in the back from the teacher. So the official definition, you can use the interference between the positive pole of the nucleus on the valence electrons. Valence electrons are like the kids in the back of the classroom, and the nucleus is like the teacher. All the electrons in between are like the kids, and they're shielding those kids in the back, the valence electrons, from the pull of the nucleus or from the teacher. Now, cesium has electrons all the way in the 6th energy level, so those kids are pretty far away from the teacher. They're 6 rows back. Lithium has valence electrons that are in the 2nd row back, or the 2nd energy level. So there aren't as many kids in between, so the teacher can do a better job watching. So cesium has a greater shielding effect because there are more electrons in between the nucleus, the teacher, and the valence electrons, the kids in the back, because cesium's valence electrons are in the 6th energy level. Lithium's valence electrons are in the second energy level, so there aren't as many electrons in between. Next question. This is asking you to kind of summarize what's going on with all these different trends. The first one is atomic size. How big is the atom? As we go across a period, imagine going across group 2, or period 2, from lithium all the way over to neon. It's going to get smaller. Now the reason the atom gets smaller, it's kind of counterintuitive. You think we're adding more protons, adding more electrons, it would get bigger, but it's the opposite. It gets smaller because as you go across, there are more protons in the nucleus, and that does not change the size of the overall atom much. Actually, at all. It just increases the size of the nucleus slightly, but it has nothing to do with the size of the electron cloud. But what does affect the electron cloud is that there's a greater pull from the nucleus. The nucleus gets stronger, so it pulls on those electrons that are in that second energy level, and it pulls on them more and more and more and pulls them in closer to the center. So the atom itself gets smaller because the nuclear pull is stronger, pulling the energy level in closer to the nucleus. As you go down a group, the size increases, and this is kind of just common sense. As you go down a group, you have more and more energy levels. So the atom gets bigger and bigger and bigger the more energy levels you add. Ionization energy. This is how much energy we use to steal or remove an electrons. So if some bad guy came in and tried to steal a kid from the classroom, the teacher would try to put up a fight and keep the kid in the classroom. Would the bad guy have to use more or less energy to steal somebody on the right of the periodic table versus the left? Well, the right means that not only are there more electrons, but there's also more protons, and we can consider protons as teachers. The teachers are stronger, so it's going to be more difficult for a person to come in and steal a student when there's a greater positive pull from the teachers or greater positive pull from the nucleus. So as we go across, there are more protons in the nucleus, so the pull from the nucleus on those electrons that they're trying to steal is stronger. And it requires more energy to remove electrons from atoms with that stronger nuclei. So more protons, stronger nuclei, harder to steal, so we need a lot of energy. It increases. As you go down a group, the bad guy would need less energy to come in and steal somebody from the bottom of the group or the back of the classroom than from the top, closer to the nucleus or closer to the teacher. So less energy is needed to steal electrons away from an atom as you go down a group because the electrons get further and further away from the positive pole of the nucleus. The nucleus can't put up as much of a fight when it's dealing with valence electrons far away than when the electrons are closer. So it requires less energy, so it decreases. Alright, electronegativity values is how strong or how well will somebody do in a tug of war for shared electrons. So imagine there's an electron between two atoms. Who's going to get that electron? Are they going to get it completely and steal it entirely, or are they going to have to share it but share it unevenly, or are they going to lose and not get to hold onto that electron as much? Now atoms going across a period, as you go across to the right, they do a better job in this tug-of-war game. They do a better job pulling on these electrons because they have a stronger nucleus. There's more protons in the nucleus, so they're stronger, and they do a better job pulling on that shared electron than the weaker nuclei, the ones on the left side of the periodic table. As you go down a group, the strength gets reduced. They don't do as good of a job pulling on electrons because the shielding effect is so high. There are too many electrons in the way because you're adding more and more and more energy levels as you go down. So there's a greater distance between the nucleus and the energy levels, or in the valence electrons that you're pulling on. And finally, number 63. What happens to the size? This one's kind of common sense. Cations, metals, they are going to lose electrons. They become positively charged. They lose their electrons. And obviously, if you lose electrons, you're going to get smaller because you're basically losing an entire energy level. Like sodium, sodium ends in 3s1. It doesn't want that extra one electron in the third energy level, so it kicks it out. There goes the third energy level. Now you're down to energy level 2, and it gets smaller by a whole energy level. Anions, these guys are gaining electrons. And remember, they're gaining more negatives. Negatives don't like each other. They're going to repel, and they're going to spread out even more. So if you gain a lot, like if you're nitrogen and you gain 3 extra electrons, that's going to spread out a ton compared to chlorine and only gaining 1 electron. So as you go across, you're going to be gaining electrons and you're going to be increasing in size.